Okay, example 3. Before we actually start example 3, let's just take a step back and discuss the production of metals in general using electrolysis. So metals, we haven't talked about metals at all. The other two examples were on hydrogen gas and oxygen, sorry, not oxygen, chlorine gas, but electrolysis is actually one way that you can use to produce metals. And the reason why you have to do it is because if you think about it, metals tend to exist in the form of an ionic compound. This is why we learned ionic compounds in Unit 1. So electrolysis is a way to essentially reduce the metal ions back to pure metals. So these are some examples of ionic compounds. So for example, if I have PbS, this is when Pb is like an ion, a 2 plus ion, and it exists with S2 minus ions. So if I want to produce pure lead, one way is to do electrolysis. I don't think they actually do this for lead, but you could. So you can apply an electrolytic cell to this ore and then just force electrons into the ion here, and then you get Pb pure form. So you can use electrolysis to produce pure metals from the ionic compounds. Anyway, in order for electrolysis to occur though, the metal ions must be liberated from the ionic lattice. So remember the ionic lattice? Let's say, for example, I have a sodium chloride ionic lattice, which is probably the most commonly found form of sodium, I think, is going to be in sodium chloride. We're supposed to have a lot of water, like seawater. So let's say sodium chloride. Pop quiz, which one is the sodium ion? So the sodium ion is going to be here, Na+, and chloride ion is the green one. So when you look at an ionic solid, which is, for example, sodium chloride, it is a lattice. So you have alternating structures. And if you want to actually reduce the sodium ion to pure sodium, you need to first of all release this ion from the lattice. So you can't actually put this in a solid. It's not going to work too well because things can move and then things like that. All right, so there are two ways to release the ions from a lattice. The first way is to dissolve it in water. So I can dissolve, I can put this lattice, this solid, in water, and you're going to get Na plus. What is that? Okay, Na plus, and then it's going to be surrounded by H2O, forming ion dipole interactions. If anyone remember, good job. You're going to need ion dipole interaction next unit when we look at proteins anyway. Oh, can't wait for proteins. Right, so the sodium ion is going to be surrounded by the negative oxygen of the water, and then similarly the chloride ions on this side is going to be surrounded by the hydrogen. Okay, so you can dissolve the salt in water. You're going to get a solution, but the ions will be liberated. That's one way. But hopefully you can see there are some issues with this already. Essentially, if you dissolve the ionic compound in water, water will be present. And this doesn't work all the time because not every ionic compound is water soluble. But if you do this, you basically have NaClAq. So you have three things present, Na plus, Cl minus, and H2O. Alternatively, you can melt the solid ionic compound. So basically apply extreme heat. I think sodium chloride melts at around 600 degrees Celsius. So if you do that, you're not going to have any water present. You're just going to have Na plus and Cl minus, and you need a very, very high temperature to keep them from reforming, recrystallizing into the lattice again. If you're going to melt it, the state of sodium chloride is going to be liquid. So liquid means molten ionic compound, means that water is not present. And you're going to have to be very careful when you write the state here. If you just write AQ, and it's actually quite hard because I think we're so used to writing AQ. But if you write AQ when it's actually molten, it's wrong, and I can guarantee you it will be marked wrong and you get penalized for it. So Na plus and Cl minus liquid. Okay, so this requires a higher temperature. This is not going to happen at 25 Celsius degree. It's not going to happen at 100 Celsius degree. It is fairly expensive to do so, and it's also quite dangerous because you have to sustain a very, very high temperature to keep the not solution, to keep the liquid ionic compound. But there are two ways. So if you want to induce electrolysis, you need to choose. You either dissolve the ionic compound in water, or if for some reason you don't want water to be there, or if the ionic compound is not dissolved in water, the other way is to melt it. There are other ways to produce metals besides electrolysis, but if you want to go with electrolysis, you have to think about these things. However, let's talk about why we may absolutely have to melt the substance and we cannot introduce water. It's because if you think about these metal ions, so let's say I want to produce sodium. Let's go back to the sodium example. And I need to essentially reduce sodium ions to sodium. I cannot do it if water is present because these metal ions are weaker oxidizing agents than water. So if you have reduction in the presence of water, water is just going to react instead. So if you want to be able to reduce these metal ions to the metal form, you need to use the molten version of the ionic compound to make sure that water is absent. Anything that's below water, all the ions that are below water on the electrochemical series, could only be reduced if water is not there. So if you want to produce a manganese, aluminium, magnesium, sodium, calcium, potassium, and lithium, you need to use the molten version. So you need to melt the ionic compounds. And actually, I think at least for this one and this one and this one, electrolysis is actually the common way to produce the metal. So they just melt it and it's a really high temperature. So the production of these metals via electrolysis would require a molten electrolyte. Okay, and the reason is because these metal ions are weaker oxidizing agent than water and can only undergo reduction when water is absent. Okay, so we're going to specifically look at production of aluminium using electrolysis, and that is example 3. And let's just talk about aluminium for a little bit. Now, aluminium you can find from bauxite, probably is the most common ore of aluminium, but there are some other. I think you can get some of it from this silica or something. Anyway, there's a fair bit of bauxite in Australia. So there is a process which we don't look at, but again, it's a very interesting process. There is a process to extract and essentially convert bauxite, which is the ore, it's quite pretty, to alumina, which is the ionic compound. Alumina, or aluminium oxide, it's essentially a solid containing Al3 plus and O2 minus. So this is your ionic compound. This process in itself is a miracle. It's great. I think it's called the Bayer's process, but unfortunately not part of the VCE course, so I'm not going to talk about it. Just want you to appreciate all the chemistry that comes in to just go from here to here. All right, so as we just discussed earlier, in order to produce aluminium, I need to melt this I need to melt this oxide. I need to melt alumina. Now, there is a problem with this, and the problem is that alumina or aluminium oxide melts at 2072 degrees Celsius. So you think 600 degrees bad? This is extremely high, and the process is extremely dangerous and expensive if you just melt pure aluminium oxide. And because of this, I think people discovered, so people knew how to make aluminium since the 18 something, but just because they could make it in the lab doesn't mean it could be commercially produced, because the melting temperature is so high that for a very long time they could produce it, but it was so expensive, and it was valued more than gold and silver. So that was back in the 18 something. I can't remember, like 1850s, let's say. So something must have happened, right? Because you can go to Coles and buy it for like $10. And what happened is these two people happened. So Charles Hall, and I'm not even going to pronounce his name because I can't, he's French. This guy was American. So they essentially, and it's quite interesting because these two people were born on the same year, died on the same year. I don't know whether they knew each other, but they were from two different countries, and they independently came up with this method to improve the production of aluminium in the same year as well. Oh my God. All right. So basically, what they discovered or invented, they didn't invent this material, they just discovered the use of it. It's cryolite. Now, cryolite is it's a very rare ionic compound. So this is the formula of cryolite. You do not need to memorize this. And what they discover is if you mix this ionic compound with alumina or aluminum oxide, it actually lowers the melting point of both. So when you can melt the mixture, and it's going to melt around 950 to 1000 degree, which may seem really high, but it's actually a significant reduction compared to the original melting point of alumina. And it is still used to this day. This is how people make aluminium, like the aluminium foil that you have in your kitchen. It's basically so they mix cryolite, which is this, with alumina, which is Al2O3, and that lowers the melting point. So just to make a general point, and because you don't have to memorize any specific examples of these cells, but if you see a cell that has something else mixing in with the electrolyte, especially if it's a molten cell, most of the time that is to lower the melting point, because this is probably one of the things that people are still looking for ways to improve. So if you can, and by the way, these two people came up with this method when they were like 24 years old, and then they became very rich. I'm pretty sure Charles Hall became really rich. I'm not sure about the other guy. But if you could come up with another method to lower this to say 100 degree, actually, I think that would be amazing if you can reduce it to that. But if you can reduce the melting temperature even further, that will save even more money. So there you go. You can do that for your career if you want. Anyway, the actual cell is actually called the Hall-Heroult. Heroult? French speaking people can correct me. Production of aluminium using this cell. I love this cell because, okay, I'll show you in a second why I love this cell, but this is a molten electrolyte. So this is not aqueous solution anymore. Carbon electrodes are used, and the electrolyte is molten alumina dissolved in molten cryolite, or that. I always think that it just looks like a person wearing sunglasses. Yeah. If you actually know what this anime character, who this person is, good for you. You can comment below, please. Anyway, so the purpose of the cell is to produce aluminium. That I'm sure that has been established in the last 5 minutes. Let's talk about operation. Okay. Um, Identify cathode and anode. I think I kind of already did it for you. This is a very interesting design. So the two, you may think that these two, one of them is cathode, one of them is anode, but that's not it. They are both anode. They're both carbon. Actually, everything's made of carbon, both the cathode and the anode here. So you have the anode up here, and then the carbon cathode is actually down here. So this is a very interesting design feature, but the diagram already identified for you, so I'm not doing anything. Write the half equations. Okay, this cell in particular, you are not required to write the half equations from scratch because it has a very unusual reaction. So one other way that I could ask this question of writing the half equation, especially when you have an unusual reaction, is I'm going to give you the overall equation and you need to be able to extract the half equations from it, even though this overall equation is wrong and that's supposed to be liquid. Okay, let's change that to liquid. So if this is the overall equation, the question is, can you write the half equation? I hope you can, and if you don't know where to start, you really want to just start by finding oxidation numbers to know what is oxidized, what is reduced. And another thing that I could do, because this is liquid, I could actually dissociate the ions to Al3 plus. So 4 Al3 plus, whoa, I was going to write AQ there. And 6, yeah, 2O3, 6O2 minus liquid plus 3C. So I'm splitting the ionic compounds into its ions. I'm allowed to do it because it's liquid. Going to 4Al liquid and 3CO2. Also, this is probably easier. This will make the process of finding oxidation numbers easier. So let's just find oxidation numbers. See how these questions are so good in the sense that they can assess so many different skills, and especially your ability to know which skill to use when. If you see an overall equation, they ask for half equation, just find oxidation numbers. When in doubt, find oxidation number. I think the original version of that was when in doubt, find the number of mole, but I don't think, oh, number of mole is coming back soon. Stay tuned on Thursday when maths come back to chemistry. All right, so these are the oxidation numbers. You can clearly see that aluminium is being oxidized from +3 to 0. So the oxidation process is Al3 plus. Be careful with the state. Going to a, did I just say oxidize? I mean reduce. That's terrible. Reduction, the reduction process. I've been talking for an hour and losing my mind a little bit. So 3 electrons going to aluminium. So that's reduction. The oxidation is actually very, very interesting here. And again, I will not expect you to be able to write the oxidation half equation without the overall equation. But it's actually a reaction between oxide ions and carbon going to CO2. There's a 2 here, and then you need 4 electrons so that the charge is balanced. So let's think about how that works in the cell. So in the solution, you have your alumina. So the aluminium ions in the solution, it's going to get reduced at the cathode. So and then you get some aluminium being produced here. Okay. Do I have room? Oh, good, good. Okay, so that's aluminium ions. It's gonna go down here, come into contact with the cathode and produce aluminium. So you have a layer of aluminium at the bottom, and then it comes out here. So where does a carbon come from? This carbon. Now this carbon, so because you have the oxide ions that is left in the electrolyte, this oxide ion is actually going to react with the anode. So this is very interesting because this is the first cell in which the anode actually reacts and get consumed, because you essentially are dissolving the carbon anode into carbon dioxide gas, which is why you can see in this diagram you have bubbles coming out. It's bubbles of O2. You may get some carbon monoxide being produced if you don't have enough oxygen present, but the main product is going to be CO2. So the anode is going to be dissolved, and one feature of this particular system is you have to replace the anode, and there are multiple ways to do it to save time and everything. But the anode is not inert in this case; it actually reacts in the equation. The cathode is inert though. So there's that. That's where the carbon come from. This carbon is actually the anode. Again, I will not expect you to be able to come up with this without the overall equation. All right, what's next? Describe flow of ions. So that's actually, I don't think you have to worry too much about flow of ions, simply because everything is happening in the same compartment, like chamber. So you only have to worry about flow of ions if you have 2 separate compartments, because you have to make sure there isn't a buildup of ions. But if everything's happening in one reaction chamber, it's not going to be a big deal. What is probably more, what am I doing? Okay, I have no idea what this is. Do I write it here? Sorry, going back to this. The collection of materials. So the molten electrolyte, molten aluminium, I need to fix that slide. Molten aluminium is going to come out here, as I mentioned earlier. And the reason for this is because, let's just cross this out. Aluminium melts at around 600 degrees, so it will be liquid in the cell. So this is very smart, as the design of the cell is very smart, because the cathode is down here. So the aluminium ions will be produced around here, and because it's melts at a lower temperature. Remember that this cell operates at around 950 to 1000 degrees Celsius. So at around 600 degrees, which is the melting point of aluminium, this thing is going to remain liquid at 950 to 1000 is what I'm trying to say. Also, aluminium is more dense than alumina. I think that makes sense. A metal tends to be more dense than an ionic compound. It's going to stay at the bottom, so it's not going to float up. So when you separate the cathode and the anode in this way, you actually also allow you're actually making sure that the product of electrolysis, so the aluminium and then the carbon dioxide, which is going to rise up, it's going to be very hard for these 2 products to come into contact with each other. So this is using the fact that aluminium melts at a lower temperature than the cell, using the fact that aluminium is more dense than an ionic compound, and using the fact that the other product is a gas, that allows you to have a natural separation between the two products, the aluminium and the carbon dioxide, without needing to build a diaphragm or membrane or layer. So you can save some money there. So that's how the material is collected. Aluminium melts it here, and it's going to, I'm pretty sure I wrote it somewhere. I don't know what happened to that particular slide and why it's not here, but it's liquid, so it's actually, it just gets sucked out of the solution. So Al liquid is, I'm just going to write it here, out of the cell. You should read your slide before you record videos. That's what I'm going to tell you. Okay, so a question that we can ask relating to the third point is, describe how this cell prevents the products of electrolysis from reacting spontaneously with each other. This is essentially what I just said. So if you really want, you can read this. So cathode is at the bottom of the cell. That's the first thing. Molten aluminum is produced when it's denser, and it remains there because it's denser than the electrolyte. So that's the second thing. The other product is a gas. So you have to really think about the states of the products, because that will play a role in all the strategy of the cell. Everything should be thought out to the point that you can take advantage of the state of the product if possible. If that allows you to save money and you don't have to build an extra component, you would do that. So the gas will go up here, whereas the aluminium stay at the bottom and get removed. And you can also remove aluminium as quickly as it's produced, so you can prevent the level of aluminium to rise up to the point when it may come into contact with carbon dioxide. So if you continuously remove it, that's another thing that you can do as well. Is that it? That is it for example 3.